welcome to the deep dive. Today we're looking at something that honestly sounds a bit like science fiction. Teaching AI models, these LMMs, to truly think with images, not just, describe them.
Right. We're going deep into the source material on a system called vThinker.
And for a long time, the central problem has been this kind of disconnect. A model can look at a picture and give you an answer, but when the reasoning gets complex, it starts to, well, they call it hallucinating.
It does. It falls back on what it expects to say based on its text training, not what it's actually perceiving in the image.
So it's a language prior problem.
It is. And the sources frame this so well with quote from Aristotle. The soul never thinks without an image. That's really the core of the paradigm shift we need.
We need an AI that uses the image like a scratch pad.
Exactly. A workspace to actually solve the problem. And that's what vThinker is designed to be. It's a reasoning assistant built for interactive, vision-centric thinking, and it learns this through end-to-end reinforcement learning, which is key.
Okay, let's unpack that, because this core concept is fascinating. vThinker treats reasoning as a code-driven visual process. So at each step, when it's thinking, it generates two things. It's textual thought, like an internal monologue, and also a piece of executable code.
And that code actually runs.
It runs in a sandbox, and this is the crucial part. It physically updates the image. Maybe it draws a line or highlights a section. So the next image the model sees is the one it just edited.
It's a feedback loop. Think, edit, look again, think. It's externalizing its own thought process onto the image for you to see.
Which is a real evolution. I mean, you look at the history here. Early models were just vision-assisted.
Right. They needed the image to get context, but they didn't really use it.
Yeah.
Then you had milestones like OpenAI's O3, which introduced basic tools like cropping or rotating. That was a step.
A move towards vision-centric thinking.
Yeah.
And then models like Time started generating code.
They did, but those operations were often, a bit disconnected, not part of a broader interactive reasoning chain.
And that's the limitation vThinker seems to be addressing. The sources say previous tools, like the auxiliary lines in Deep Sketcher, were just too rigid.
Very tightly coupled to specific tasks. You couldn't generalize them. And the image-to-code pipelines, they often struggled with spatial accuracy. You'd edit something and suddenly the geometry is just slightly off.
And that tiny error would just derail the whole reasoning chain.
It kills it. So vThinker isn't just a new model, it's a whole post-training paradigm built on two huge components. First, something they call a Data Evolution Flywheel.
Okay.
And second, a visual progressive training curriculum. It's this integrated approach from the data all the way to the final alignment that's so interesting.
So let's start with that Data Evolution Flywheel. The sources say this is what's needed to create data that can generalize across all sorts of real-world tasks.
Right. You need data that hits three targets: diversity, quality, and importantly, difficulty.
And this is where the paradigm really flips. The model stops being a solver of problems we give it.
And becomes a creator of its own.
They mention using strong LMMs, like GPT-5, to directly generate Python code that renders completely new images, the diagrams, the entire reasoning path. And the quality was supposedly better than what humans could create.
Which naturally brings up a question, right? If the model is making its own training data, doesn't it just get stuck in a repetitive loop?
How do you ensure creativity?
That's the diversity stage, or what they call knowledge-driven evolution. They use these foundational knowledge concepts, things like drone views, physics, math, and visual tool systems as anchors.
Okay, so like building blocks.
Exactly. And these two systems, the knowledge and the tools, they co-evolve. They generate new counterparts for each other and combine in new ways, constantly creating a stream of diverse data sets. They ended up with one called V-Interaction 400K.
So the building blocks themselves keep it fresh.
They do. Then comes the quality stage, coordinating calibration. This is basically a big quality control mechanism.
Because you need everything to line up.
You need coherence. So a checker component screens everything, the text, the image, and the image action connection. But here's the clever part.
What's that?
Sometimes the model's final textual answer is wrong, but the visual steps it took, the lines it drew, are perfectly logical. In that case, a repairer doesn't throw the data out.
It fixes it.
It reconstructs the original question to fit the valid visual reasoning path, so you don't waste any of that high-quality visual data.
That's really smart. Okay, and then you have the difficulty stage, progressive expansion. This is about making the problems genuinely hard.
It is. It's about extending the chain of thought, forcing longer reasoning. They use two strategies here. First is parallel extension.
Which is simpler?
A little. It's just adding new constructions, like a new line, that are independent of what came before. But the second one, sequential extension, that's where the real complexity comes in.
How so?
Here, the new construction depends on the result of the previous step. For example, the model first draws an auxiliary line, let's call it DM. The next sequential step might be to draw a new line that has to be perpendicular to the line DM it just created. It forces the model to track and use its own intermediate results. That's how you get those really challenging problems.
All right, so they've engineered this perfect data. Now, how do you actually train a model to use it? That brings us to the visual progressive training curriculum.
Right. And the curriculum absolutely has to start with what they call perception alignment.
Why there?
Because even these really powerful LMMs are, frankly, pretty bad at fine-grained spatial perception. They struggle to pinpoint the exact location of a corner or an intersection in a busy image.
It's a failure of attention.
It is. So to fix this, they created another dataset, vPerception 40K, just for point-level supervision. They structured it across 3 dimensions: how elements relate, how many elements there are, and what knowledge concept it is.
And they even control the number of elements.
They did, sampling from a normal distribution centered around 8 elements. It ensures a good mix of simple and complex scenes.
And the tasks themselves are tiered, right? It's not all of the same difficulty.
No, it's progressive. You start with surface-level tasks, like just identifying coordinates. Then you move to the semantic level, like finding the top left vertex of a shape. And finally, you get to integrated reasoning, which combines perception with computation.
So you make sure it can see properly before you ask it to start drawing.
Exactly. And once that foundation is there, you move to the second stage: interactive reasoning alignment. This starts with supervised fine-tuning, just to get the model used to the tools, and then it's followed by reinforcement learning.
Okay, so RL. But how do you reward a model for something like drawing a line? That doesn't seem like a typical RL setup. What's the reward function?
That's a great question. The system uses a sandboxed environment to run the code and a specific algorithm called GRPO, but the reward function is the key.
It must be complex.
It's actually composed of 3 parts. Accuracy, so did it get the final answer right? Formatting, did it output it correctly? And tool usage.
Ah, tool usage.
Yes, but here's the catch. The tool usage reward is only given if the final answer is correct, and the model used at least one tool to get there.
So it's actively incentivizing the model to get out of its text-only comfort zone.
It forces it to show its work visually.
Okay, so does all this actually work? The sources introduced a new benchmark to test it, VTBench. What stood out to me here was the rigor.
It's expert verified.
5 domain experts looked at every single sample, and a task only made it in if at least 3 of them agreed that visual interaction was absolutely necessary to solve it.
You couldn't just guess from the text. And the results on VTBench really show how big the problem was. Existing LMMs, even state-of-the-art ones like Qwen 2.5 VL, they struggled.
What were the numbers like?
On the instruction-guided interaction domain, that model scored just 8.8% accuracy.
8.8%. That's a huge gap.
A massive gap. It shows the difference between general visual understanding and actually being able to think interactively.
And vThinker's performance.
It consistently outperformed the baselines. In that same difficult domain, it saw an over 25% performance improvement.
So that really validates the whole approach. The interactive ability is the missing piece.
And the ablation studies confirm it. When they took parts of the curriculum away, performance dropped. Removing the RL training caused a more than 6% drop on benchmarks like Math Vision. Removing the initial perception alignment did too.
So every piece matters. The data, the order of training, all of it.
It's the whole package, and the qualitative results really show it. vThinker forms this think-edit loop where it's autonomously generating code, rendering the edited image, and using that to move forward. It's literally drawing its way to the solution.
It's using the image as a scratch pad.
It is. It simplifies these really complex chains of reasoning that would just overload a purely text-based model. vThinker really is a successful formalization of this idea of interactive thinking with images.
So what does this all mean for the future? Where does this go?
Well, the sources are very upfront about a key limitation, which is computational cost. The current version of vThinker is still limited in its scale.
It can't be applied to everything just yet.
Not yet, but they leave us with a really provocative thought. They suggest that as our base models get more powerful and we get more computational resources, this whole paradigm, the data construction flywheel and the upper limits of model reasoning, should be constantly re-examined.
So as the base models get smarter, the data flywheel can generate even better, more complex training problems.
Exactly. The system's own capacity for teaching will grow right alongside the model's capacity for learning. And that's the ongoing challenge for anyone trying to build systems that can achieve truly human-like visual interaction.
That's the end of this deep dive.